Up until this point, we've talked about solubility equilibria in terms of an ionic compound that was seemingly insoluble. We've kind of examined the fact that it's not completely insoluble. That is to say, some ions will in fact go into solution, just not very much, right? So you often have mostly solid in your solution, but there are still some ions that go into solution. And that's what we've been talking about with the solubility equilibria. Now, in this video, I wanted to kind of get into a couple of factors that affect the solubility equilibria. And this is in section 17.5 in your text. And so there are three main points that will affect the equilibria. And they all come down to Le Chatelier's principle. Okay? So the common ion effect, we already talked about at the beginning of this chapter, but I'll go over how it affects solubility equilibria. So that will change how soluble or insoluble a particular ionic solid is. pH can also affect the solubility equilibria of a particular compound. Essentially, it's the same type of effect as the common ion effect, but now with pH, we are examining specifically the H plus and the OH minus in our solution. And then the last factor that we'll talk about briefly is the formation of complex ions. And this is just the tendency of a metal ion to form a complex ion that has its own formation constant, which can affect the overall equilibrium of a different ionic compound containing that metal. Okay, so let's start with the common ion effect. So if we have, let's say for instance, if we have a solution of silver nitrate, okay, whoops, a solution, here we go, a solution of silver nitrate, okay, and this is very soluble, okay, so we have silver ions and nitrate ions in this solution, okay. So if we were to take a different silver compound, let's take silver chloride, which actually has a pretty low solubility. It's 1.6 times 10 to the minus 10 for its KSP, right? So you have some solid going into this solution to form a small amount of Ag plus and Cl minus. Now, if we were to set up an ice table, okay, if we were to set up an ice table, having added this solid right here, adding this solid to this first solution here, right, where we had Ag plus and NO3 minus in solution, right, so that means for this equilibrium, or this ice table, if you will, we're going to just do a qualitative ice table for this example. If you had an ice table for this equilibria, then you would have some X amount of Ag plus to start with for this particular equilibrium, right? Some X amount, not zero, so our Cl minus would still be zero, but we have some X amount that came from this species right here, right? So it's this Ag comes down and is already in your solution, right? Already in your initial solution of your compound, right? So if you were to increase, and if you want to have your your KSP would be, our KSP, what did I say, is 1.6 times 10 to the minus 10, right? 1.6 times 10 to the minus 10. If you were to have this species dissociate, it would not dissociate enough it would not dissociate much because there is already some Ag plus in solution, right? So this is the common ion effect, where if you have a little bit here, it's going to push the overall equilibrium back towards the reactant side, right? So then you would have to suffice with to say that the amount would have to come down, the amount of Ag plus either would have to come down or up by not very much, right? It would be up by some other, let's choose another variable, plus y, if you will, plus y. So then our concentration, our equilibrium concentration would be x plus y, right? And then y for the chloride ion, right? But the y would be smaller than if we had just put some silver chloride into water solution, okay? So this common ion here is making this overall compound here less soluble overall. That is to say that less of the AgCl will dissociate into Ag plus and Cl minus, okay? All right, so now let's talk about pH as it affects the solubility equilibrium. So pH will be similar to the complex ion effect, or excuse me, the common ion effect, which we just talked about in the last slide. So the pH, though, like I said before, it will be in direct comparison, observing the H plus and OH minus, and how each one of these, H plus or OH minus, will affect the salt that goes into solution. Okay, now let's take barium hydroxide. So if you were to take barium hydroxide solid, right, and put it into some water, right, pH 7, okay, then this would dissociate into barium 2 plus and 2 hydroxide ions. Okay, now what if we put it into a basic solution? If we put it into a basic solution, similarly to the last example, right, with the sodium chloride, or excuse me, the silver chloride, if we were to put this into a basic solution, we would have already some amount of OH minus already in solution, okay? So we would have some X amount of OH minus, hindering the dissolving of this barium hydroxide compound going into the equilibrium, okay? So if it's in a basic solution, this particular compound would be less soluble, okay? Now, what if we put this same barium hydroxide into an acidic solution? What would happen then? Well, the formation of the 2OH minus, right? This 2OH minus would come from the barium hydroxide dissociating into water, right? This 2OH minus would interact with the H plus that's present in that acidic solution, okay? So we have that acidic solution already having this H plus in solution, 2OH minus reacting with 2H plus to make water, right? In fact, there would be two waters that would be formed there, okay? So if you were to put barium hydroxide into an acidic solution, the OH minus would get quote-unquote eaten up, right, by the H plus. The OH minus would get used up by the the H plus, forming more water, which drives the overall equilibrium towards the products in our first reaction, right? So the overall equilibrium will drive this way, right, if you are in an acidic solution. Let's keep our color scheme the same here. In an acidic solution, it will drive this way because the OH minus will react with the H plus to form H2O, thus taking it out of this equilibrium overall, right? Taking it out of this equilibrium overall. And remember, if you decrease the concentration of a product, you will drive the overall equilibrium towards the product side. So this will result, if you put barium hydroxide into an acidic solution, this will make barium hydroxide more soluble. So let's look at a compound now that does not have the hydroxide ion in it, right? So let's look at barium carbonate. Okay, now if we were to put barium carbonate into water, right, we'd get barium 2 plus and then the carbonate ion to some degree, right? To some degree. Now, if we put this into an acidic solution, right, an acidic solution with excess H plus, okay, now this excess H plus is very important here because then you have this carbonate anion will actually interact with that excess H plus to form HCO3 minus, right? And we know that this right here is a weak acid, so this absolutely has the capability to be reformed once it's in solution, right? Weak acid. And then to go even further, because this is a polyprotic, this could even interact with another H plus to form H2CO3 or carbonic acid, right? Could go even further, just from the nature of it being a diprotic acid. Okay, so if these subsequent equilibria come about from the formation after the formation of the CO3 2 minus anion, right? So since this anion gets taken out of this first equilibrium, right, the overall equilibrium will shift towards the reactant, or towards the product, excuse me. So the whole equilibrium will shift towards the products if this is in an acidic solution, giving the carbonate ion something to interact with. So it shifts towards the products in an acidic solution, making this particular compound more soluble in acid or an acidic solution. Now I do want to point out that obviously not all ionic compounds will have this effect, right? So if you have something along the lines of, say, calcium bromide, right? So this would dissociate into calcium 2 plus 2 bromide ions, right? And just like we've dealt with this with salt solutions creating acidic or basic solutions, right? Br minus, because it is the conjugate of a strong acid, conjugate of HBr, it will not reform HBr, just from the fact that HBr in and of itself would dissociate fully and not produce an equilibrium, right? So the fact that the Br minus here, it is a conjugate of a strong acid, it won't interact with water or acid in to any extent. So this calcium bromide would not be affected by an acidic solution. There's no effect.